Hello everyone, this is Mr. Life Changer again. Okay, in this video I'm going to continue from where I stopped in the last class. Okay, um, in the last video we started a series for 30 questions on electric current and cells. So this is a continuation to that. Now this question here says four identical cells, each of EMF 1.5 volts, are connected in series. The total EMF of the combination, ignoring the internal resistance, is, now whenever you have EMF, let's say you have this, another cell here, another cell here, another cell in series. This is 1.5, 1.5, 1.5, 1.5. Now the total EMF is to add up everything. So that's going to be 1.5 plus 1.5 plus 1.5 plus 1.5. And that is going to be 6 volts, which is VD. Now, but I want to bring something to your notice, very important. And that is to say that the orientation matters. Orientation. What I mean by the orientation is that, we have positive and negative. Now, the one side is longer, the other side is smaller, positive, negative, positive, negative, positive, negative, positive, negative. Now, but if the orientation is different, you have to subtract. Like if I have something like this, look at this, then this is, did you notice the difference here? Positive, negative, but this is negative, positive. So if this was 1.5 volts, 1.5 volts, 1.5 volts, it means that the total EMF is going to be 1.5 plus 1.5 minus 1.5. You are going to subtract the other one whose orientation changes, and so the total EMF is going to be 1.5 volts. Please note this. This is extremely very, very important. Okay, and in case you are also asked to calculate the total resistance is also, internal resistance is also R1 plus R2 plus R3 plus R4 and so on and so forth. The internal resistance, the orientation does not affect internal resistance, so there is nothing like minus. The orientation only affects the EMF. Please note that. Okay, so that leads us to the second one. This one says that three cells, each of EMF 2 volts and internal resistance 0.5 ohms, are connected in series and supply current to an external 4.5 ohms resistor. Calculate this current in the circuit. Quite easy. We have three cells, so we assume here that they are all in phase, in the same phase. So since you have three cells, the total EMF and they are in series is E1 plus E2 plus E3. Okay, that is going to be 2 plus 2 plus 2, that is going to be 6 volts. And the total resistance, because they are in series, internal resistance is 0.5 plus 0.5 plus 0.5, and that is going to be 1.5 ohms. You get it, right? Okay, so, and we are given that it is connected to an external resistor R of 4.5 ohms. Quite easy. So here we are asked to find the current in the circuit. I already showed you in the other video that the current in the circuit is the EMF all over the external resistance plus the internal resistance. So that is going to be 6 over the external is 4.5, the internal is 1.5. Okay, so that is going to be equal to 6 divided by 4.5 plus 4.5 plus 1.5 is going to give us 6. So 6 divided by 6 is 1 ampere. So the answer to this question is 1 amperes. This was wrong. 1 amperes. Okay, so I hope this makes a lot of sense. Now the next one says four identical cells, each of EMF 3 volts, are connected in parallel. The total EMF of the combination is, now this is important, as long as the cells are in parallel, like this, please note this, as long as the cells are in parallel, the total EMF is equal to one of them. So this is 3 volts, 3 volts, 3 volts, 3 volts, and I'm asked to find the total EMF. The total EMF is going to be just one. Just pick one out of it, which is 3 volts. So the answer is C, 3 volts. As easy as that. Please do not miss that. But if you were asked to find internal resistance, for example, just like we would see in the next question, 1 over R is going to be 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. That would help you find the internal resistance since they are in parallel. Okay, I hope this is helpful. Now, number 14. Two cells, each of EMF 1.5 volts and internal resistance 2 ohms, are connected in parallel and supply a 3 ohms external load. We have an external load. The current through the external load is, now watch this, the two cells are in parallel. Note this. So the EMF is going to be equal to pick one of the cell, just one, okay? So which is 1.5 volts. Then the internal resistance, since they are 2, you can just simply say 2 times 2 over 2 plus 2, which is 4 over 4, which is equal to 1 ohms. Okay? Now, you can also, if you like, you can say 1 over R is 1 over 2 plus 1 over 2. Okay? So 1 over R is equal to 1. So R is equal to 1. If you want that, you can do that. Okay? Then the external resistor R is equal to 3 ohms. So with this now, we can say that the current is equal to E over the external resistor plus the internal resistor. Your E is 1.5, the external is 3, the internal is 1, right? So that will be 1.5 volts. Okay, 1.5 volts divided by 4, and this is going to give us 0.15, that is 375, I guess. So the answer to this question is C. So please discard this. That is not correct. If I want to put this in a diagram, it's going to look like this. It's going to look like this. Then the bolts are connected to the load resistor. You can do this. This is 1.5 volts, 2 ohms. 1.5 volts, 2 ohms. Then the external resistor is 3 ohms. That's if I am to represent this information in a diagram. Okay, so kindly note that. Now, the number 15 question looks quite somehow. A 12-volt battery and the internal resistance is 1 ohms. Note that is connected to the following network: a 3 ohm resistor in series with a parallel combination of a 4 ohm and 12 ohm. What is the total current supplied by the battery? Very easy. If I should put this in a diagram, I'm going to have my 4 ohm here and 12 ohms here. This is 4 ohms. This is 12 ohms. Now remember, it's supposed to be in series, okay? Yeah, in series with a 3 ohms resistor. I could actually bring this first, but that's fine. So this is, we have the 12 volts voltage here, and the internal resistance is 1 ohm. So the first thing is for us to find the total external resistor, which from what we have here is 3 plus 4 times 12 over 4 plus 12. So that is 3 plus, this is 48 over 16, and that is 3 plus 48 over 16 is 3, I guess, and 3 plus 3 is 6. So 6 ohms. So now we can find the current. The current is E over R plus R, and so the E is 12. The external resistor R is 6, plus the internal resistor is 1. You can see that. That is quite easy. I hope this is correct. 48 divided by 4 times 12 is 48, divided by 16 is 3. I hope this is correct. 3 plus 3 is 6. Okay, so this is 6 plus 1. Okay, so that makes it 12 divided by 7. And 12 divided by 7 is about 1 point, 1 point. We don't have the answer here. There is no answer here. So the closest answer is this, which is 1 point. Something. I can't do that here now. You can use your calculator to get that value. But the most important thing is know how to go about this, okay? Now, number 16. It says in question 15 above, the potential difference across the parallel combination is, okay, so we want to know the potential difference across the parallel combination. Now, the only way we can know this is if we find, first of all, the lost voltage. Now, I mean the terminal voltage. Terminal voltage is I times big R, okay? Or let's rather do it this way. Let me call this V1 and call this V2, okay? So V1 is equal to the current times R1. V2 is equal to the current times R2, okay? So the current, let's assume that the current is 1.5. I'm just assuming, okay? So my current I, the current is 1.5 times the R1. This whole combination, I can call it my R1, and this whole combination, I can call it my R2. So the combination here gave me 6 ohms, so this is times 6. That will be equal to, I think this is 9 volts, okay? And here IR2, the current is 1.5 times R2, which is 3. This is going to be 4.5, I guess. Yes, 4.5, okay? So this is the answer. And please note here that this plus this is not going to give you this. No, never. It's not going to give you that. It's not the same thing, because the voltage across here, remember, this internal resistance has reduced the voltage supplied by the cell. So that is what that should be. Very important. I don't know, I have this instinct that I have made a mistake somewhere. I'm trying to find out what the mistake is, but I can't see any mistake here. Okay, so let's proceed. Okay, I can't see any mistake here, so let's proceed. Now you see 9 volts, so the answer, the current, the voltage across this is 9 volts, so that's what we are going to choose, 9 volts, which is C. Okay, then number 17 here says a current of 6 amperes enters a parallel combination of 2 ohms and a 6 ohm resistor. The current through the 6 ohm resistor is quite interesting. So you have a current, let me draw this. This is 2 ohms and this is a 6 ohms resistor, and here I have a current of 6 amperes. Now the first thing to do here, I'm not giving the voltage, so we could find the voltage if we want. Now, but I wish I can show you a shortcut to go about this. Okay, maybe I should do that. There is a rule called current dividers rule. The current dividers rule, you can use it to divide a current across two resistors that are in parallel. It's only used for parallel combination. And so in this case now you can say I1 is equal to R2 over R1 times R2 times current I. Then I2 is equal to R1, this is plus, R1 over R1 plus R2 times the current I. So if I call this my R1 and call this my R2, that means the current flowing through here is I1 and the current flowing through here is I2, okay? That is important. Now they said we should find the current through the 6 ohms. So through the 6 ohms here is I2. So if I want to find this, I'm going to start with R1, which is 2 ohms, over R1 plus R2, which is 2 plus 6, then times the total current, which is 6. So this is going to be 2 over 8 times 6, okay? So that is going to give us 12 over 8, which is 1.5 amperes. So the answer to that question is 1.5 amperes. Now this rule is not O level, but you you can learn it. It's very easy. It's called current dividers rule. You can use it to divide current among two parallel resistors. Okay. Now we have the next question here. It says, according to the maximum power transfer theorem, maximum power is delivered to a load of resistance when the load resistance is equal to the internal external source. Please note that. So maximum power transfer happens when capital R is equal to small r. That is when a cell delivers maximum power. R equal to R. That's an important exam question. Now the next question here says, a battery has an EMF of 10 volts, an internal resistance of 2 ohms. What is the maximum power that can be transferred to the external load? The formula for maximum power, okay, is equal to the square of the EMF divided by 4 times the resistance. Please note that, divided by 4 times the resistance. Remember that maximum power, capital R equal to small letter r. So the EMF is 10 here, so 10 squared over 4 times 2, that would be 100 over 8, and 100 over 8 is going to give us 12.5, so 12.5 watts. That the answer is C. Kindly note that, very important. Then number 20, which is going to be the end of this session. A fuse is a safety device that, a fuse, okay, we have different options here, but the answer to this question is B. A fuse is a safety device that melts and breaks a circuit when current exceeds a safe value. In our next video, we are going to see some the rest of this session. We are going to see some calculations involving fuse and fuse rating. Okay, so the answer to this question, a fuse actually melts or breaks when too much current is passing through it. It helps to safeguard, other devices. So I'm going to stop here. You are going to meet me in the next video. This is 30 questions, so this is just the first video is 1 to 10, this is 11 to 20, then the last one is going to be from 21 to 30. Okay, so see you in my next video. Okay, bye.